I mean, this vanishing gradient problem, it's a problem really with, I mean, it has, if we can discover it, it will be very, very good. But if we cannot discover it, it will have maybe a catastrophic impact on some people, right? If we are building a model and this model should be used somewhere, so we need to be sure that our model works fine. So I mean, if partial E by partial omega equals 0, in this case delta omega will be 0, and we will prevent our weights from training. So and it's a problem especially for weights of the front layer. And when those weights in the front layer will not be able to train or change, so the front layer will transfer random inputs to proceeding layers. So this is a problem. So if we have some weights of input layer is random values, so in this case, the model will just see random values, right? And this is most difficult problem from my point of view.
So the way to check this might be to output the weights and see how they are moving, or?
Yes, I guess we need to check. Maybe you can plot the weights, for example, check if the weights are changing, for example, or otherwise it will be a problem.
So we have to check if they are changing from random to something constant, or I mean, improving, not having random values in every layer.
Yes.
Yeah. Okay.
Mm-hmm. We talk also maybe we talk already about the batch gradient and the stochastic gradient. So maybe we talk about this one. I mean, batch gradient, it looks like an old man moving carefully and wisely, right? When it's batch gradient, so we will not have this kind of because when you have too much energy, you have energy enough, you can explore lots of areas around you, and you can move from this one to this side, and you can just look here and there. So it's not random walk, but it will be more careful walking. So batch gradient, you can just consider it like an old man moving. So he want to save his energy, and at the same time he take his wise decisions, and he just move in the right direction with less noise. So we minimize the cost function by taking a step in the opposite direction of the cost gradient. I mean, this is gradient descent, and it's very computationally expensive, especially for large data sets with millions of data points, where we need to evaluate the whole training data set each time we take one step towards the global minimum. So it's very computationally expensive because we are not doing it example by example. We need to upload all our data points in the memory. We need to calculate the gradient for each example, and after that we need to take the average gradient and use this average gradient for calculating only one delta value, and adjusting the weight only one time each epoch. So in batch gradient, we can just say that delta omega equal eta multiplied by the mean gradient, this one. So this is the equation, Ali, which you have been trying to get. So we have this eta multiplied by delta, for example, mean, for example. So we need to do this one. So each time for each input, we calculate t minus y, multiply this one, and get the mean at the end, and after that calculate this delta omega and use it for adjusting the weights. But in case of stochastic, we do it example by example, and therefore they call it online learning. We don't need to keep all those numbers in the memory, because if you want to calculate y, for example, so I need to get x for this y and apply it to the model, go forward, find y, go backward, calculate t minus y, keep all this in my memory, and at the end I need to calculate the average gradient and use this average gradient for adjusting the weights. So it's very demanding computationally.
When we dot product two vectors, the output is just one argument, and the meaning of one argument would be the same argument. So maybe the problem in our code.
So no, it's according to how you want.
I'm sorry.
It's how you will implement it. So for example, you can multiply it point by point and calculate.
I just do the dot product again, but instead of me,
you can do it like this one.
Yeah.
Just multiply row by column, and in this case, the output will
that's okay. I'm okay.
And so, divide it by n.
Oh yeah, that would be right. Yeah.
Yes. So just do it like this, for example.
Oh yeah.
In a stochastic gradient, it's eta multiplied by, for each example, t minus y multiplied by x. And in a stochastic gradient, it's recommended to use this, way for selecting adaptive learning rate. We call this one adaptive learning rate. Adaptive learning rate. So adaptive learning rate, it will be, we select eta as a function of the number of iterations. We start with large value, and after that, we reduce this one when we are close to this saddle point. So because at the beginning, number of iterations equals 0, for example. When number of iterations equals 0, it means eta equal C1 divided by C2. So now we start by large value. You can select, for example, C1 equal, for example, 1, maybe C2 equal 1, for example, or C1 equal 0.8, C2 equal 1, correct? So in this case, we can start by 0.8, and when number of iterations increases, eta decreases. So this is adaptive learning rate. So when we use adaptive learning rate, we start with big eta, big learning rate, and reduce it with the number of epochs. And it's logic, because when we train the model, we need to start with big values, big step, and when we are close to this point, we need it to be just a very small one, so we can sure that we will reach this bottom point here. So it's recommended to use with the stochastic gradient descent to try to use adaptive learning rate. Adaptive learning rate, it should be function of number of iterations, for example, and someone else, maybe he can just say, okay, I will select it as a function of the absolute value of the gradient, right? Because at the beginning, the gradient is very large, and when we reach here, the gradient becomes very small, becomes 0. So you can select it as a function of the number of iterations. Maybe someone else can select it as a function of the gradient, for example, right? So stochastic gradient descent, they call it iterative or online gradient descent, and it's like maybe drunk man moving down a hill, right? So he is moving maybe in stable and powerlessness, for example. So he just move in different directions. Maybe you can just say a young guy, very young, and he has lots of energy, for example. So he can explore. He has too much energy. He can explore around him. So the learning rate will be noisy. So how can we select it? When we use this adaptive learning rate, for example, it decreases over time, and C1 and the C2 are constant values. So we need to select C1 and the C2, and eta will be selected as a function of based on this number of iterations. So we can be sure that we will have big step at the beginning, and after that we will decrease it with time. Yes, mini batch gradient. It's like young man moving down a hill. I mean, it's a trade-off between the two options, between a stochastic gradient descent and the batch gradient descent. Number of mini batches will be the size, data size, divided by the mini batch size. No, this is the number of updates. In fact, this is the number of updates. So I have my data points. We have one block. You can just divide this block into small blocks, mini batches, right? And we will train the model. I mean, we will work with mini batches, and the batch size or mini batch size, it's according to your memory size, in fact. So maybe you can start first by batch gradient, and maybe your computer will crash down, for example. So in this case, my memory has a problem here, and it's better to just use mini batches. So you need to select a mini batch size, and in this case, in each epoch, we will update weights by number of batches, number of mini batches. How many batches? It's the data size divided by the mini batch size. We can get number of batches. This one, it's a number of batches, in fact. Number of batches or mini batches, right? So I had a problem, in fact, maybe 2 years ago. I had a problem, and I give that, because the exam was written some years before, and I'm just asking students to calculate how many times we will update weights. In case of stochastic, in case of batch gradient, in case of mini batch gradient. So for example, if we will use number of epochs 10, if we have 10 epoch, if we will train the model for 10 epoch, if we are using a gradient descent, batch gradient, how many updates, weight updates? So if the number of epoch is 10, how many times we will update weights?
It depends on our
10 times.
So
Yeah, because we will update one time each epoch. So in this case, it will be 10 times. Correct? Okay.
I'm sorry, I'm not following this mini batch learning. Can you explain?
So I mean, if you have a model and we need to adjust, we will train the model for 10 times. If it is batch gradient, we will update the weights 10 times, only 10 times, one time each epoch. And if it is a stochastic gradient, and for example, the data size is 100 data points.
Mm-hmm.
So in this case, in mini batch gradient, how many times we will update the weights?
100.
100 each epoch, correct? 100 times each epoch. And if we will train the model for 10 times, for 10 epoch, so it will be 100 times 10, so it will be 1,000 times. Correct? Okay, what about mini batch? If the batch size will be 50 points, so we have two mini batches. In this case, how many times we will adjust weights? How many times?
500 times? No, I don't know.
One more time. We have 100 points. We divided those 100 points into two mini batches. So we have two mini batches. So how many times we will adjust weights? We will update weights?
Twice.
Twice in each epoch, 2 times each epoch, correct? 2 times each epoch. So in total, it will be 20 times. Right?
Yeah. So we require more epochs when we use mini batch learning.
No. I mean, if you will train them, I mean, when you are training your model, you select maximum number of epochs, correct? So if I told you maximum number of epochs is 10, and if you will go for example, stochastic gradient descent, so how many times we will adjust weights, we will update weights, it will be number of data points times number of epochs. So it will be one time. If you will use batch gradient, in this case, all data points will be just one batch. In this case, we will update weights only one time each batch. So how many times we will update weights? It will be 1 times 10, correct? 1 times 10. If it is mini batch gradient, and we divided the data points into two mini batches, so in this case, we will update the weights 2 times each epoch, right? So in this case, in total, how many times we will update weights? It will be 2 times 10, which is 20. So the batch size, how can we decide the batch size? It's according to your memory. So I mean, the ideal case is that we will go for batch gradient, right? Because we need to be like an old man who is wise, he is moving wisely, correct? He selected in each step by thinking. So in this case, maybe the ideal way to go for batch gradient, but we need to consider using a mini batch gradient when my memory when we have an issue with the memory, right? So this is very important. Okay, so it's just maybe it's batch gradient is applied. I mean, you can play with those. You can just select an example and try to apply batch gradient, stochastic batch gradient, mini batch gradient, and just make comparisons. And we have some examples here. Comparison between batch gradient and the stochastic gradient. In fact, do you see here in this graph? This one, it's a stochastic gradient, and it's clear. We trained the model for number of epochs, maybe 70, and this curve, it's so if you cannot see this one, okay, I will just hide this one. So this one, if you see this error curve and this error curve, can you select which one is batch gradient, which one is stochastic gradient? Which one is batch gradient?
Yellow one.
So this one, it's batch gradient because it's not noisy and it's smooth and right like this. But this one, which is noisy one, this one it's for stochastic gradient, right? So and this is the performance of the model. So this is, we trained two models here. This is one model. I don't know which one belongs to what. Maybe this one belongs to stochastic gradient. This one belongs to batch gradient. So in batch gradient, we have smooth error surface. Require the more epochs. We need to have more epochs. Computationally expensive in terms of memory need. So it's just connected to the memory. And of course, the memory, it's connected to the data set. How's the data set look like? Is it just numerical values? So if you have only numerical values and the Excel files, numerical numbers, we don't have any problem to go for batch gradient. But this patch gradient, it will be a problem only with people who are working with videos and images, right? So if you are working with YouTube videos, if you are working with text, for example, so in this case, we need to have big memory. SGD, it's noisy and it's fast, it converges maybe faster, and it's suitable for online learning. Online learning is very important. So imagine that you are building a system which will allow people to get access to the building, right? But by facial recognition, for example. So I don't need, when I have new one coming to my work, I need to give him access. I don't need to retrain the model using the whole data points again. I need to retrain the model using the specific one which we have received. So online learning, it's very, very important, right? I don't need to add him to the data and retrain the model because it will cost us too much time. But I will just train the model using this single example. This is very enough. It's important for something called open set data sets and stuff like this, because sometimes we have, I build a model and we have new examples coming in. So those new examples, we need to train the model using those examples. So it will be very suitable for online learning. Yes. Yes. So maybe I need to remove those annotations. Do you have any questions for that part?
I have one, if I can ask.
Yes.
What is the deal with Adam optimizer? Is it better than stochastic gradient descent, or because the models which I've been making now with LSTM, every paper says to use Adam optimizer, ADAM.
They use what?
Adam, ADAM optimizer instead of stochastic gradient descent.
I mean, did you see any difference when you tried the two optimizers? Can you see any difference?
Yeah, I haven't tried till now, but when you started presentation last week, I was looking at the thing, and then I tried to compare what I was actually using. And the LSTM's example, I found they all used another optimizer instead of stochastic gradient descent. But it's fine. We don't need to discuss that now.
Yeah. We will discuss those optimizers. So we will have 1 week. We will compare between different optimizers, right?
Okay.
And try to find the difference. But usually people go for testing, maybe trying different types of optimizers and see which one is performing better.
Yeah. Okay.
Yeah.
Okay.
So because we need to have some presentations today, maybe some of you can prepare some project presentations, because we had 3 2 weeks ago. So we need to get some presentations of project also today. Maybe we will have at the end maybe 30 minutes or 40 minutes for some presentations. So, but today I want to go quickly to this sklearn. This one, it's fantastic in Python. Sklearn, it's very important. It will help us. It has lots of models, lots of optimizers, so we can work with it at the beginning. So we want to use it for maybe iris classification problems. If you want to, how can we plot the decision boundary? How can we split data into training and testing? It has a function for doing this, and it has also a function for splitting the data it's for cross validation. How can we work with multi-class classification problems? I told you about this technique which called one versus rest. We talk already about logistic regression classifier today, and we compared it with adaptive linear unit. How can we use logistic regression for iris data set, separable and inseparable data sets, confusion matrix? This is very important. And we need to talk about multi-layer neural network. So before studying deep learning, we need to use first this MLB, right? Because this MLB, you can take it deep as much as you want. Also, we need to use MLB classifier in sklearn and in Keras also, right? Because Keras is very important. We need to use Keras in deep learning. So we need to know how can we build MLB in Keras, how can we build MLB in sklearn, for example. So this library is very important. It has lots of very nice stuff, in fact, classifications, the regression, for clustering, for example, and you know the difference between classification and the clustering, right? So what is the difference between classification and clustering?
Clustering is unsupervised.
Yes, clustering it's unsupervised, but classification it's supervised. We have also here dimensionality reduction, BCA, model selections, data pre-processing, right? So it has lots of stuff, in fact. So this one is very, very good. Very, very good library, in fact, in Python. So you know iris dataset already, right? You know it. We have petal length, petal width. We have sepal length and sepal width. We have three classes. We have iris, setosa, versicolor, and Virginica. So we have three. We have three here, three classes, right? So and when we use a perceptron, because perceptron we can use it for binary classification. A perceptron, adaptive linear unit, or logistic regression, it works only with binary. So we just selected setosa and versicolor. We selected the first 100 points. So the first 100 points, it's for setosa and versicolor. And you can select. I mean, here for simplicity, I'm just using two features, two input features, because I need to plot it in two-dimensional space. But if you want to use 3, 4, it's fine. So when you want to use the 4 inputs, it will be the same. We will just have the same model, but we will have 4 inputs instead of 2. So we will have here x1, x2, x3, x4. We have here the bias, this one, and this function here. If it is perceptron, this one will be step function. If it is adaptive linear unit, it will be linear function. If it is logistic regression model, it will be this sigmoid, right? So in fact, if you want to build a model, you can do it like this. For example, if you want, you can have a perceptron, you can have adaptive linear unit, you can have also logistic regression model. But remember, it's binary classification. So the output here must be only 2 cases, 0 and 1, for example, right? So one class will be represented as +1, the other class will be represented as 0. So for example, we can say, okay, setosa will be +1, versicolor will be 0, right? So in this case, we can use this model for solving this simple problem. Here, I'm using sklearn and I'm using linear model. I'm importing perceptron. Maybe from now on, you don't want to implement stuff by yourself because it has already implemented here, right? And also those optimizers, you can just pick it from the library and just use it. I mean, but it was important to understand the concept, how those stuff works. So from sklearn, you can import a perceptron. You can import adaptive linear unit. You can import a logistic regression model and just test it. So first, we need to load our data set. How can we get the data set? We have something called data sets in sklearn. These data sets, it has almost, I mean, many things, in fact. Lots of public data sets which we need to use. But if you have something specific, you can upload it to your in your code. So just upload data, try to visualize the data, pre-process it, for example, standardize, normalize, and after that, build, select a model, baseline model. It's not the best model ever, but it's just a baseline model. So for example, in this example here, we need to standardize for example, this is the part for data pre-processing. From sklearn also we can use pre-processing. So first I uploaded my data point, data upload. So and after that we need to pre-process my data points, for example. So I will just I have x here, x equal I guess it's petal length and the petal width, for example. So this is my x. I need to standardize it. So I will use this standard scalar from sklearn. Import standard scalar from sklearn. And this is how we make it. So x standardized, it will be we need to to initialize this standardization standard scalar, for example, and just to do it like this. So now it's standardized. When it's standardized, it means it has a mean of 0 and a standard deviation of 1. Standard, it's not normalization, it's standardization. The standardization, it means all my column will have mean equal 0 and standard deviation equal 1, right? After that, we need to get a model. So just you can import a perceptron. We got a perceptron from sklearn.linear model. You have a perceptron. So model equal perceptron. There are lots of issues here. In fact, you can define many things you can define here. So for example, you can define maximum number of iterations, the learning rate, this random state. You can also select, because we need to validate, when we train the model, we validate the model. Do you remember? So the validation ratio here, you can select the validation ratio here, for example, 10%. because we divided the data point here into, for example, if we will go for hold out validation, we need to divide the data. We didn't do it here, in fact, but we need to divide my data into one for training, one for testing. Part from this training, we will use it for validation. So when we divide the data into training and testing, you need to select here the validation ratio. It could be 10% from the training data set, for example, for validation. And after that, fit your model or train your model using X standard and Y, and you can just make some predictions. Of course, maybe I have some problem here. This one should be X standard because we trained the model for X standard. If you train the model for X standard, you need to predict using X standard. Otherwise, we will have a problem, right? And you can plot model coefficient and model intercept. Model coefficients, it means it's the weights. Model intercept, it's the bias. You can get the bias and weights. So for example, in this example, we just use the two inputs. So we should accept that we have omega 1 and omega 2, and we have bias. Prediction error, it will be the difference between y minus y predict. We can get y predict here. So we can get the mean value of this one squared, right? So it will be the prediction error, for example. So, but this is not correct, as I told you, because here we didn't divide the data into training and testing. So it's very important to divide your data into training set, testing set, and the validation set. If you want to validate your model, in here you need to define the validation ratio, right? You need to select the validation ratio.
Our data is not shuffled, is it?
Yes, we didn't shuffle. We didn't. I mean, all
we need to shuffle too.
Yes, of course, but we have a function here. We have a function here which it's called the training test split. If you will use this function, it will shuffle automatically. You don't need to shuffle.
We used it last session.
Yes. So if we use this train test split, you don't need to shuffle because it will automatically shuffle your data points. But here we didn't shuffle. We didn't do anything in the correct way, right?
Right. Another thing, what is the function of transform on X? Because we fit the
this one.
Yeah.
It's for standardization, to standardize all data points. You can write a code for doing that part, right? So this one, it's
and fit and transform both are for standardization. Okay.
Yes. It's this. We import this one from pre-processing, scalar node pre-processing, and it will standardize it automatically, column by column. So it calculates the mean value, standard deviation, and it will apply the formula to standardize all inputs. So, and finally we can plot the decision line. So this is the decision line of my data points, right? How can we do it? It's the same as I told you. Also, the same equation here. I described it that last time. So I mean the equation of this line, it's omega. This one I will just call it x1. This one it's x2, for example, right? So the equation of this line will be omega 1 x1 plus omega 2 x2 plus b equals 0. And if we have x1, just assume values for x1 and get x2 from this equation and plot x1 and x2 to plot this decision line. So using this one, plot x, y, this one. So once you define the x1, we can get x2 from this equation. Is it okay? So x2 will be minus omega 1 divided by omega 2 times x1 minus b divided by omega 2. So this is the equation for getting it. So if you have x1, we can get x2, we can plot x1 and x2 to plot this decision boundary. So, and we can see that the line is a very nice line. It can differentiate, it can divide the two classes into two separate classes. So this is, I don't know which one is blue, which one is red. Maybe this is Setosa, maybe this is versicolor or whatever. So this is +1 class, this is 0 class. Right? So plotting the decision line, I can plot it using this way, which is nice. It will make this pure line. It looks very beautiful line. But if you want to get a graph like this one, in this case, we need to write a function. For example, call it plot decision boundary region. It's also easy because we have here x1, we have here x2. So we will assume values for x1 and x2. It will be all numbers between x1 minimum and the x1 maximum. with this step, for example, x2 also we will generate values for x2. We create a grid, for example. So we create values like this one. We create in the other side, we create other values for x2. So we create this grid, and in this grid we have lots of points here, right? We just send all those points to the model and find which class this points belongs to, right? So we create lots of points. We send those points to the model for predicting. We created this grid from x1 and x2. We created this grid. We send those points to the model to predict the class and plot those classes using a contour function, this contour f function. So at the end, we have all those data points here belongs to this class. All those data points above the point, the line will belong to the other class. So it's easy to plot this decision boundary in many ways. Yes. Splitting the data into training and testing, this is very important. As you mentioned, Ali, we didn't divide it. So this is wrong. If you wrote a paper like this one, it will be rejected. So if you didn't divide your data points into training and testing and decide which learning mode, your work will be rejected, definitely, right? No one will accept it. So we need to follow the protocol, which we need to follow really in machine learning. So first we need to decide, I mean, which approach we need to validate our model. So if you will go for hold-out validation, so we will divide the data into one part for training, one part for testing. Is it okay? This is very basic. We can do this if you have enough data, if you have too much data. So we can, because that part for testing, we will just use it for only testing. So if you can afford this, because some people cannot afford it. So I knew a PhD student who was collecting data and he just collected 100 points. If he collected 100 points, he cannot hold out 20 data points for testing because it's too much cost. He spent too much time from his PhD. He used the money, he used the resources for collecting. So each data point is expensive, in fact. And he cannot just put it away for just testing and using only 80 points for training. So this is, I mean, wasting resources. So in this case, he cannot afford hold-out validation, and he need to go for cross-validation. So first, in hold-out validation, we will split into training and testing. That part will be used for training. That part will be used for testing. But you can also specify a part here for validation, right? Maybe 10% or 20% from the training part, we can use it for validating the model, right? Validation is very important because the validation is the only way to help us to know online while my model is in training if we have overfitting problem. We can discover it later on, of course, but it's better to discover it early to avoid it. Because maybe I'm training my model and each time it will overfit. How can we solve it? So one way for solving it is to use something called early stopping. I mean, overfitting, it means my model has very high capacity and we train it a lot, overtraining. So I need to stop training at some point. So if you want to stop training at some point, you need to discover that your model starts to overfit. How can we do this? Using the validation set. If you cannot afford this hold-out validation, we need to use cross-validation. So first, I need to discuss this function. So a train test split, we get this function from sklearn, also model selection. And it's simple. You have all data points X and Y, and you need to specify here the test size or the training size. So when we select test size equal 0.3, it means training size equal 0.7. And you need to specify this one for shuffling. This function will automatically shuffling. So you need to maybe select this random state if you need to reproduce the same sequence again, right? So for example, I used this function now, and I plot here. Do you see? I printed here the bin count in Y train and the bin count of Y test. So for example, in my data points, I have 2 classes, right? And then when we split here, we don't care if the 2 classes are equally represented in the training and testing. So from this function, we will get here Y train, we will get Y test, right? So you have 2 classes. Are we interested to have the 2 classes equally represented in the test and the train? Are we interested? because
I'm sorry, your voice
I mean,
lost for.
no, I mean if when we use this function, we will divide the data into two blocks, one for training and one for testing. And if we have in y here, if y is representing two classes, for example, so maybe we have class 1 and the class 2, for example. So maybe we are interested that the two classes are equally represented in the training set and the testing set. So
it's fairness, as
yes.
you.
So I'm printing here number of different classes in each set, in y train and in y test. So I have 36 from class 1, 34 from class 2 in the training, and in the testing we have 14 and 16, right? Which is not fair, maybe because the two classes are not equally represented. If you are interested in having the same number of classes in each set, in this case we need to use this command, stratify equal y. When we use the stratify equal y, we will get the two classes equally represented in the training and testing. So this is important. So if you want the two classes to be equally represented in the training and in the testing, we need to use this one, stratify equal y.
I'm sorry, how much this unfairness would be tolerated? I mean, how much could difference the system could bear?
I mean, for example, just imagine that I trained the model. We using this one will shuffle, right? We have two classes, so it could happen that maybe class 1 will be represented more than class 2 in the training. So imagine that this number is, because we have 50. So imagine that we have here, for example, I mean total number is 50, right? So imagine that we have here. Maybe we have here 50, for example, we have here 35. Imagine it's like this one. It means my model will be trained to classify this model more compared to this one. So imagine that it's a problem. We are getting CVs from people to get jobs. We have two classes. One class is, for example, is maybe, how can I say it? For example, foreign people and maybe Norwegian people in, applying for a job, right? And the model, we have two classes. We can just class 1 and the class 2, for example. And in the training set, maybe the Norwegian, for example, are more represented, more than foreign people. So their chances to get the job will be much higher because the model will be biased towards the class which is more represented in the data set. You can just, I mean, for example, some systems are biased against women when they apply for jobs. So you have male and female CVs, for example, and if you have more male CVs in the training data set, so the model will be more familiar with male CVs or male applicants, and it will make decision which is biased against women.
In metrics, there are some weighted, as I remember, there are some weighted metrics that could.
No, I'm not talking about the model itself now, but I'm talking about the biasness from the data. We can get some kind of biasness from the data because of this. So as I told you, we have people applying for jobs, and they discovered that, I mean, machine learning are biased against women when they apply for jobs. So if you will have CVs and the model will just decide by itself which one should get the job, I mean, the chances of male will be much better than female. Why? Because the model is biased against women.
So we should lose some of our data in order to have a fair data set?
It could be, yeah, it could be. So for example, if you have 150 applicants, male and 50 female, so now it's obvious that the model will be biased against women.
But it will be biased. It's very expensive
it will favor male applicants. So chances to get the job, it will be 3 times the females. Correct?
Yeah. So for example, about the CV, how do we choose some applicants? Like, should we ignore some applicants, Norwegian applicants?
Yeah, it could be because I need my data point to be biased, to be balanced, correct? So if you want it to be balanced, if you have 50 female, for example, you can select 50 female who are getting job and are not getting jobs, for example, and in the same way also we need to select the other one equally, right? And we need to have all classes equally represented in all training and testing. So this is very, very important if you want your model to not be biased against anyone, because this biasness, it could come from the model, right? It could come from the data set itself, right? So
Is this unfairness is about it's just about the could we ignore a feature, for example, that nationality?
This is very good, because maybe we have a feature, for example,
Yes.
make the system biased.
Yes,
so maybe sex, we can remove sex from the data set. Gender, for example, I mean, when we have the gender, we can just ignore the gender, so we can treat all people equally. So we need to identify which feature is making this kind of biasness in my model, for example. So we need to get rid of some of the features, for example. Yes. Yeah, Ahmed, do you have any question?
No, actually, this is the exact case that happened for credit scoring. It's when using neural network, and one of the solutions is the one that you have said. It was related to the nationality, like the one that were original from African origin. They have their origins from Africa. They have been rejected, and when they look at the data, they look at their data and all historical data that has been fed to the model would lead to the same decision. So one of the solutions was how can we cancel, for example, the sex and the nationality, and let's see how the model will behave. But,
and the model was performing better.
To be honest, I haven't followed the case clearly, but I can share it with you. It's a known case. If you write credit score in USA bank using neural network case of overfitting, you can find it online. But I will share it with you guys.
Yeah. It's the same. Also, there is a public data set, in fact, which is used for just the people who spend some years in the jail, for example, and the chances. I mean, they use it in courts, for example, those data sets to check if the person has, maybe he will commit another crime in the near future or something. So also they have a data set, in fact, in US, and they have been using it in courts for many years, and it's biased against the black people. So it's a huge problem, and we really need to take care of those points. At least when you are writing a paper, if you will try to refer to those cases, it will be very, very good, really. So we need to refer that we know that there is biasness. Maybe it's in the data, unbalanced data set, and we need to take care of it. Just to refer to it. Yes, you are in the train, Ahmed. Yeah.
Yes, I am in the train. Exactly. I'm coming to Olison. I'm on my way.
So we will use, so just to remember, if you will use this function here, if you will use this, I mean, train test split, remember to use stratify equal y, at least. So you need to check your data set, how the data set look like, and you need to check if there is some features we need to ignore, for example, to avoid this biasness, and build a system which is more fair for all classes which we have. In holdout validation, we need to split the data. We need to divide the data into a number of folds, but each time we shuffle. So we are not splitting. I mean, we divide the data into a number of folds with shuffling, and after that we train the model. It's the same. We divide it into a number of folds, for example, and each time we train the model with k-1 and test with k, with ice fold, and each time you will get some accuracy. So for example, I will train a model here, and I will get some accuracy here, accuracy 1, and after that you will go for the next fold, for example, next k, for example, k equal 2. We will initialize the same model, but with new random values, train the model, test the model, get a new accuracy. So in this case, we will have here 5 accuracies. If k equal 5, we will have 5 accuracies. And at the end, the average accuracy will be the average value of those 5 values. And at the end, we will use the whole data set for training brand new model.
I'm sorry, can we use a train test split 5 times for cross-validation? Like each time it shuffle the data and use like 80% of the whole data?
No, we divide it into blocks, 5 blocks, right?
Yeah, it's so like
equal 5. So we will have here 5 blocks, 1, 2, 3, 4, 5. We will train with 4 and test with 1, and we will repeat this process until we testing the model with the whole data set. I mean, the idea here is that we tested the model with all data points, right? So the accuracy here will be more realistic. In fact, it will be more.
Yeah, but instead of this specific cross-validation, we just
no, we
train.
cannot, because you don't sure. I mean, if you will shuffle each time, we will have some information leak, because maybe at some point I'm training and testing with, so it will be very problematic. In fact, we need to be sure that there is no information leak, right? So
there is no information leak in each.
No. But for example, I tested the model with that part. If you will shuffle here, and you will divide, as you mentioned, maybe we will test this model with a similar data point. We will, with some part from this one here again, we will test the model with that part, right? Part is new, part is old.
Yeah, but the model, because the model is
different
from the start, so it doesn't see.
But also you will train the model with I mean, in this case, you will train the model with part of the data set which should be tested. In fact, they call it information leak. I mean, in this case, maybe the results, the accuracy which we will get will not be very robust. So if we need to use this holdout validation in sklearn, it's simple. Just use train test split, and you will get x train, x test, y train, y test. Remember to use stratify, right? And just train your model. I mean, when you train your model, so we will train the model using x train and y train, and when we want to test the model, we will test it using x test. So in this case, you will get two error values or two accuracies, for example, two prediction error. So we will have the prediction error, training error, and test error, right? So I mean, here we use holdout validation. So we divided the data into one for training, one for testing. So from that part, we will get some error value. From that part, we will get some error value. We call it test error, for example, and this one, it's a training error. And in fact, from this training error and the test error, you can discover if you have overfitting a problem, right? From those two values. So for example, if this one is very small, this one it's high, it means we have overfitting, right? So after training your model using holdout validation, we will calculate. We will get this train error and the test error, right? If the training error is very small and the test error is very small, this is very good. But if training error is very small and the testing error it's very high, it means my model has memorized my data points and it overfit my data points, my training set. So we can discover if my model is overfitting or not from those two numbers. So those two numbers are very, very important. If this one is low and this one is low, it means it's underfitting, right? So sorry, if this one is high and this one is high, not low, I mixed it with accuracy. If training error and the testing error, both of them are high, it means my model is underfit. But if this one is very small, this one is high, right? It means we overfit my data points, my training data set. So in fact, we can discover overfitting from training set and the test set and the test error, but it's too late, right? It will be too late because my model has already trained, so I need to go retrain the model one more time. I cannot use early stopping, but if you want to use early stopping in online learning, in this case, we need to have a validation set and plot the curve. So we will have the curve for training, for validation, and if we see that the validation error started to increase, it means my model started to overfit. So I need to stop before this. I guess someone has a question.
No, I think your microphone is working.
Irina? Irini? You are muted, Irini.
Yeah.
Yes, I know. I just have a problem today with my sound and microphone. So yeah.
Okay.
So what I would ask was, if we discover that we have overfitted the model, which of the parameters that we have chosen during the training we have to change?
So overfitting means that maybe you don't have enough data points, right? So and you are using holdout validation, so you need to change the way of training your model. Maybe you need to go for cross validation, right? Because overfitting, it means I have very small data. I don't have enough data to train my model, in fact. So instead of working with hold-out validation, you can go for cross-validation, number one. Number two, overfitting, it means your model is very complex and has high capability or capacity. So try to simplify your model, right? Maybe instead of using feed-forward neural network with the 3 hidden layers, I can just go for only 1 hidden layer. Number of neurons in hidden layer, you selected 20, maybe 20 is too much. I can just select 10, for example. So try to simplify the model. Because model capacity means the model has huge number of weights, and it's very capable, in fact, which will absorb your data points quickly, and it will memorize it quickly. Look, Irini, imagine that you have a PhD student, and you just give him a test from elementary school, first year or second year, correct? He will just get 100% quickly, because he is very capable, right?
Yeah.
So if I want to test him, maybe I need to give him maybe very difficult math exam according to his level, but I cannot give him an exam with, this very, very simple one, because he will just overfit it. It's easy, he will just overfit it. So I need to increase the data size, number of data points which we have. Using a cross validation, maybe I can use data augmentation, because I need to increase the size of the data points which we have, and I need to reduce model capacity, just to try to select base model. And I advise all people to start with a simple, don't start with a complex model, because it's easy to, when you have underfit, it's easy to deal with underfit. So underfitting means my model is very simple, right? So I can just add one more hidden layer. I can increase number of neurons in each hidden layer, for example, so I can make it more complex. But when your model is too complex, I need to move in the opposite direction. So I need to make it more simple, and I need to try to use data augmentation to increase the size of my data points, for example. So it's better to start with a simple one and increase complexity until you have good performance, but don't start with very, very complex one and go into this overfitting problem and try to go in the opposite direction. So the baseline all time is much better. Just to go with a baseline model. Baseline model, just to start with a perceptron, no problem. Don't feel it's too simple. Go with the logistic regression model. Start with maybe this adaptive linear unit, for example. Feed forward the neural network with 1 hidden layer, and after that, increase complexity step by step until you achieve good performance. Another point also, you need to have validation. When you select your model, you need to select the validation ratio, right? When you have this validation ratio, you need to plot the curve. The training and the validation error. From the training and the validation error, you will discover at some point that your model starts to overfit. If the model starts to overfit, you can use early stopping. So you need to use early stopping when you build your model. When you select those model parameters, you need to activate early stopping. So the training process will stop if the model starts to overfit, because I want to train the model, but I don't want to train it too much. Correct? It's just we need to train the model, but not too much, because if you will train it too much, it will memorize the data points. It will not be able to generalize. So we can use early stopping.
Sorry.
Thank you.
In validation, when we find out that our model is overfitting, the validation is rising.
Yes. Do you see my screen now?
Yeah.
So this is the number of epoch. For example, we have here the error, and this curve. This curve. This one is training error. Training error.
Right.
So, for example, each epoch we will find calculation prediction error in the training error, and we will plot it. And of course, when we train the model more, this curve will just go down all time. Correct? If you keep training your model, this curve will go down all time. So we are expecting that the training error will decrease with time, no doubt. Okay. So on the other side, we need to plot something called the validation error. So in the validation error, we will use 10% of my training data sets for validation. So I will apply those 10% and just calculate each time the prediction error, not training. And in validation, we just test the model using the validation set. So each time, yes, I will calculate this validation error. We are expecting it also to decrease, to be at the beginning. It will be I just need to select color. So for example, Validation error here will be number here. It's big number, correct, at the beginning. And also when we train the model, this number will decrease, will decrease, will decrease. But at some point, it will start increasing. Correct?
Right.
Correct? When it's increasing, in fact, it means my model, when we keep training the model, my model just memorize the data point, and it cannot classify the validation set because the model now it's only memorizing those points. So for example, I'm overfitting. This is cup of tea, this is phone. If you give me another phone from different model, for example, I will not be able to, because I just know this is phone. I don't know. If you give me a Samsung, for example, I will not be able to say this is a mobile phone, right? Because I know that this is a phone, and I just memorize this one. So I will not be able to.
Early stopping is just for when we use validation. If we use validation, we couldn't use early stopping parameter.
No. When you use, validation. It's we need to use it anyway because this curve is very important also in your publication. So people, when they are reading your thesis, they want to see this curve because they want to be sure that your model is not overfitting. Just avoid this question from reviewer by providing this simple curve, right?
Right.
So people will see this curve and they will see, okay, the model is fantastic and it has been trained. It's not overfitting. But if you want to use early stopping, so when you select your model here, do you see those parameters? Maximum number of iterations, verbose, eta, validation fraction, random state. We have here also something called early stopping. Early stopping equal 1, for example. When early stopping equal 1, it means it's activated. And it means when the model starts overfit, it will stop training process. And it will go back maybe one epoch earlier or something. So it will give you the model here before this overfitting problem. So it will not allow it to continue training. It will stop training to avoid, being in this bad situation, for example. Because I need to stop it. The model is fantastic. It's okay. And now I need to the model with this kind of training. But if you will keep training it, it will overfit your data points and it will not be able to generalize.
Thank you.
So for cross validation, we have the same also from sklearn model selection. We can get cross validation. So it's the same. If you want to use hold out validation, we will use train test split. If you want to use cross validation, we have also a function called cross validation score. So we selected the model. My model, it's a simple perceptron. We selected maximum number of iterations 100. Learning rate is 0.01. Validation fraction is 0.1. Validation fraction, it means 10% of my training data will be used for validation, right? So when we use validation fraction, it means from my training data set, I need to keep part for validation. It will be 10%, for example, 20%. You need to decide this. So we need to use this function cross validation model for X and Y, all my data points. And this is the number of K, number of folds. CV equal 5, it means K equal 5. And we have scores. If CV equal 5, it means we will get 10 prediction errors from this one for each fold, right? So from this one, we will print it, we will get 5 values. And if you want to get the average, we can get average accuracy from this one. You can get average accuracy and also standard deviation. Those numbers are important, right? So it's not only you don't need to write the mean value, but maybe standard deviation also, because the standard deviation, if it is too much, it indicates also that I have some kind of problems. So it's important to write the mean value of the prediction error and its standard deviation. It will look more professional, in fact. And after this, now I have an average accuracy, correct? Now I need to train a model. So start your model and train it from scratch using the whole data points. Correct? Maybe I need to define the model here one more time. I don't know if we need to, because yeah. So now you train your model using the whole X and the whole Y. We don't divide anymore, because in cross validation we don't divide. We train the model using the whole data points. We train the model now using the whole data points, and we got the average accuracy from cross validation. We don't need to test the model anymore because it has already been tested using cross validation. So using hold-out validation and the cross validation in sklearn, it's a very, very simple one. Very, very simple one. Yes. I don't know why we cannot move my screen. So now, what about? I mean, so now those models we can use it for binary classification problems. What about multi-class classifications? As I told you, multi-class classification, it's very simple. For example, you have 3 classes. We can use a technique called the one versus rest. For example, one versus rest. It's very. I mean, this multi-class classification, it's easy using MLP, right? Multi-layer perceptron. So I have here 3 classes. I can just use MLB, for example. So this MLB, it will have 3 outputs, right? One for each class, for example. So for this solving this problem, I can just have multi-layer perceptron where we have 3 outputs, one for each one. So this one will be 1 when it's this one. This one will be this one when it's this one. This will be this green class when it's. So it could be the output could be like this one. But if you want to use this problem, use problem using a perceptron, we need to use a technique called one versus rest. So we will build a model to classify this one against the rest. We will get this one. We will use another model to classify this one against the rest. So we will get another model like this one. We will get another model to classify this one against the rest. So we will get one like this one. So in this case, we will get 3 models. If you want to use a perceptron. So if you want to use a perceptron or this binary classifiers, we need to use a technique called one versus rest. It will be like this one. You have, I did that one using logistic regression. For example, we have 3 classes, and if we will use this one, you have the code also here. It's called so it's make blobs data set. It's from sklearn. We generate these data sets. You can control number of data points generated. You can control the standard deviation on each class. So you can create some kind of overlap between classes. And if you will use one versus rest technique, we will get one model for each class. For example, the red one, it will classify this one against blue and green. We will get the blue model, which will classify blue against the green and red. We will get the green model to classify the green one, which is 1, and the rest will be zeros. So this is very simple technique. And this is the code for doing it. Maybe the most important here, how we use the logistic regression, right? And we fit the model using X and Y, and we select here. We use this function called make blobs. It's from sklearn datasets. So in datasets, in fact, in sklearn datasets, we have some functions which can generate some standard datasets for testing some algorithms, and it has very, very nice functions. Those functions are very nice because it's a standard. You can control it, how many data points we need to get, and the specification of the data points. So it's something very nice. Those standard data points or public data sets are important when you are working in the algorithmic development. So if you need to develop new algorithm, for example, don't use your own data sets, because if you are using your own data set, maybe the performance will be much better. You need to use something standard so people can trust that, okay, this algorithm works fine. If I need to test my algorithm against another algorithm, we need to use the same data set. So in this case, we need to use some public data sets, which is public, or some specific data sets which are generated, in fact. So other people can replicate it, right? Other people can just get those data sets easily and test your model against other models. So if you want to use logistic regression, you can also use logistic regression from sklearn in the same way, and just build your models and plot those stuff. So it's just, if you want to use multi-class classification, you just need to use this option here. So when you select your model, so you need to specify maximum number of iterations, and at the same way also you need to select if it is multi-class or not. So this one, it's one versus rest. This OVR, it's one versus rest. If you want the model to deal with multi-class classification problem. So at the end, I will get 3 models. In fact, so I'm using this one here for 4 classes. So in this case, we will get 1 class for each data for each class, 1 model for each class. And each model, we have 2 inputs. We have x1 and x2. So in this case, in fact, each model has only 2 inputs. Omega 1, omega 2, x1, x2. We have here bias. So we will get 1 from those models for each class. So we should expect that we will get 4 models, 1 for class 0, 1 for class 1, 1 for class 2, 1 for class 3. This is omega 1, omega 2 bias, and we can plot those decision lines. So it's one set of classes, one set of algorithms which we need to test, and now we are done with it. We are finishing it with this multi-class classifications. So we can use a perceptron. So people feel that a perceptron cannot be used for something really strong and difficult problems. No, we can use it for multi-class classifications. We can use it for solving really very difficult problems. After that, we need to work with multi-layer perceptron, right? If you need to solve the same problem using a multi-layer perceptron, I just told you, we need to have different layers, and we need to have one for each. This one, it's multi-layer, in fact. So we have maybe one output layer, one input layer, for example, and we will have one output for each one class. Yes. So maybe we can. So maybe we can. I mean, I don't know. Should we take some presentations from you, for example, and we can continue the rest next time? Is it okay? I mean, next week we will finish this slide and we will talk about multi-layer perceptron. We will have it here, in fact, some examples for multi-layer perceptrons from sklearn, for example, and the week after, maybe we can start talking about deep learning. But this introduction is very important. So I mean, people can, we can have some good understanding of those basic stuff. So now we're moving on the track, starting by perceptron, those simple models, and after that we can go into MLB, using MLB for solving different types of problems, and after that we can go into deep learning, for example. So should we stop here, or should, I don't know, we need to have some presentations from maybe 3 projects, for example. So can anyone, if he is ready, can just raise your hand, please. So we can have maybe 5 minutes break, and after that we can go for project presentation. But we need to know who will present today. Okay, so Ali, he will have presentation. Who else will present? Just 2 slides or 3 slides about your project.
I can do mine.
Okay, thank you very much.
Yeah, I can do mine as well.
Okay, can you
Magnus.
Okay, Magnus. Yes.
I don't think I'm able to raise my hand for some reason, but
okay, thanks, Magnus. Yeah, so we have 3 projects, so we can take maybe 4 minutes break and start exactly at 11:30 with Ali, for example. So you will have we will have 30 minutes. So you have maximum 10 minutes, Ali, please. So maybe just 8 minutes presenting your project, and maybe 2 minutes for questions. Okay, so thank you very much. So we will meet again after 4 minutes. You can just bring your coffee. Yeah. You can share also your screen, Ali, until we get coffee.